All right, guys, let's go. My name's Harkness. I'm here with Shutter Network, and Shutter uses advanced cryptography to make your favorite platforms more fair and credibly neutral. Now, it's really early in the morning, so I'm not going to take you through any crusty advanced cryptography. Instead, let's play a game. Who wants to play a game? Wonderful. You can play later by yourself. This game is super complicated. It's super complex. I think I'm going to have to take a minute to explain the rules. It's called rock, paper, scissors. Anyone ever heard of it before? Okay. Well, the rules are pretty simple. You've got two players, and on the count of three, each player shows his or her hand. You've got a couple choices: rock, paper, and scissors. So rock beats scissors, scissors beats paper, paper beats rock. If there's a tie, you do an instant rematch. Pretty simple, pretty fair. Okay. But let's switch it up, and we're going to change one important rule. We're going to introduce an important element: information asymmetry. Awesome. So now when we're playing this new game of rock, paper, scissors, player one is going to show his or her hand on the count of three. And then the next player is going to be able to look at their hand, count to 3 seconds, and then choose their hand. Now, who wants to play this new game, information asymmetry, as player one? You want to play? Well, that's too bad. No. I love your enthusiasm, but no. Player one is going to lose every single time. It's not just that they are at an inherent disadvantage. The fact that the other player can see their move and then choose their own move means that player one is going to lose every single time. Player two is going to win every single time. Now, this is a really stupid game, and I'm sure that no one here wants to play this game, but the fact of the matter is that most of you play this game of information asymmetry all the time, and you do it on chain. Here's one example: front-running and sandwich attacks. If you are doing a DEX swap and you submit that trade to an unencrypted mempool, you're basically revealing that trade publicly on chain, and you're giving the opportunity for searchers and block builders to look at your transaction and place transactions either in front of or both in front and behind your transaction. And by doing so, they're able to manipulate the price of your transaction, and they're able to give you a worse price, basically stealing money from you. In fact, front running is, by definition, someone seeing your transaction and putting a transaction in front of it based specifically on that information. Another example is DAO voting and manipulation. So if any of you are a part of a DAO and you have a forum where you can discuss and a platform where you can vote, a lot of times you'll notice that you can see each and every vote as they are cast in real time. You can see whether a person voted yay or nay as soon as they cast their vote. And that opens the door to a bunch of different types of manipulation. The first type is that a bunch of whales could all vote in a specific way, let's say yay. And they do so immediately, and so smaller token holders look at that overwhelming yay vote, and they think, there's no way that we can defeat this proposal. And so either they just vote yay, or they get dispirited and they don't vote at all. Another possibility is that a voting whale would sit on the sidelines And they would basically just watch to see what the smaller holders do with their votes. And if it's going their way, they don't need to do anything. But if it's not going their way, at the very last second, they can cast the determining vote. And we've actually seen this play out on platforms time and time again. And it actually has a real-world impact. In the case of front-running and sandwich attacks, billions of dollars are lost each and every year. And when it comes to DAO voting, hundreds of thousands or even millions of dollars changes hands depending on the results of these votes. So let's fix this game. Let's introduce something called a commit and reveal scheme. And a commit and reveal scheme is exactly what it sounds like. You get both of the players to commit to their moves, right? And we'll lock them in place, and then we will reveal them. This way, no one has the benefit of information asymmetry. But who's going to monitor them? Who's going to enforce this commit and reveal scheme? Well, let's introduce a trusted third party, right? Give it up for trusted third parties. No. The whole reason we are in crypto is because we don't like trusted third parties, right? It is against the core ethos of blockchains and crypto. And there's a couple of reasons why. When you introduce a trusted third party, yes, you might solve one problem, the problem of information asymmetry, but you're introducing other problems. One problem which you might introduce is corruption. Let's imagine we're playing a very high-stakes game of rock, paper, scissors for $100 million. If I was player one, I would be willing to bribe the trusted third party for $99 million if it meant that I could take home $1 million. And I, as the trusted third party, would find it very hard to resist that temptation of accepting that bribe. So even with a trusted third party and bribery, we still get back to the problem of information asymmetry. The other problem is centralization, because when we introduce a trusted third party, they are put in a position of power. They can extract value or money, and by utilizing that power and money, they can entrench themselves and become even more powerful, and it becomes this downward cycle of more centralization, more power, more centralization, and so on. So, what do we use if we're not using a trusted third party? Well, this is where Shutter comes in. We're introducing a credibly neutral third party. And here's how it works. We still have this commit and reveal scheme where the players lock in their moves, they commit to them, and then once all of the players have locked in their moves, then we reveal them. That way no one benefits from information asymmetry. But instead of having a single trusted third party to do this, we use a decentralized keeper set. And they generate encryption and decryption keys using threshold encryption, which is X of n. Here we're introducing an assumption that there is an honest majority of keepers and that they are faithfully generating encryption and decryption keys. But we're not just trusting them. We have a number of mechanisms in order to enforce this. One of those is snitching, where if a keeper does try to collude, another keeper can snitch on them and get a reward for doing so. And then another one is staking and slashing. So the keepers themselves need to stake some money in order to be a keeper, and also members of the community can stake in order to vouch for and say that they have good faith in a keeper. If any of those keepers collude, then their stakes are slashed. So let's go back and apply this idea of a credibly neutral third party to some of these examples that we talked about earlier, starting with front-running and sandwich attacks. Shudder has shielded trading on Gnosis Chain, which we launched in July of this year, and it's pretty simple. A user submits their transaction, such as a DEX swap, and it gets picked up by an encrypting RPC, which uses the encryption key generated by the keeper set to encrypt that transaction. And then the encrypted transaction is added to the public mempool. A builder takes that and confirms the place of the transaction within the block. And since the transaction is encrypted, the builder doesn't know the contents of the transaction. So they just put it at the top of the block. Then the validator works with the keeper set that generates the decryption key to decrypt the transaction, and the transaction is added to the chain as normal. Another example is DAO voting and manipulation. And Shudder has shielded voting on Snapshot. We launched it in October 2022, 2 years ago, and it has already protected 634 DAOs. It has encrypted 300,000 transactions, and 87% of DAOs who try out shielded voting are still using it 1 year later. And it's similarly simple. The user submits his or her vote. It gets picked up by Snapshot Hub, and it is encrypted using the encryption key. All of the votes are collected during the voting period, and when the voting period ends, then Snapshot Hub and the keepers work together to decrypt the vote, and everyone can see the results. One of the really nice things about shielded voting is that although the content of the vote is encrypted, you can still see how much voting power was deployed, and so you can know whether or not that particular proposal has reached quorum. So, that is a quick introduction to Shudder, which, as I mentioned, uses advanced cryptography to make your favorite platforms more fair and credibly neutral. If you run a platform, please reach out to us, and we would be happy to help you introduce a credibly neutral third party in order to make your platform more fair for end users. And if you're an end user, you can go to Gnosis Chain or Snapshot, and you can protect yourself from sandwich attacks and front running, and also from DAO vote manipulation. If you'd like to learn more about any of the topics we discussed here today, head on over to shudder.network. My name's Harkness. Thank you so much.